Okay. When you're comparing different gases because of different densities, because of different partial pressures, different masses, we have to make sure that the conditions in which we're measuring these are the same. And the conditions vary based upon things like temperature, pressure, volume. Temperature implies water vapor pressure differences. And there are 4 conditions that you will see utilized or talked about or whatever. Ambient temperature, pressure, saturated. What's the temperature in the room? What's the water vapor pressure? What's the barometric pressure? Ambient temperature, pressure, dry, meaning now I've removed all humidity from whatever these ambient conditions are. Standard temperature and pressure, dry, which I'll talk about. And the one that we most frequently are working with is body temperature, pressure, saturated. So what's inside of our body. So in the case of ATPS, ambient temperature, pressure, saturated, I would need to find out what the room temperature is and what the barometric pressure is. From that, then we can look on that chart and determine how much water vapor is present. Dry, there's no water vapor pressure, so we can ignore that. STPD is the weird one. Standard temperature and pressure dry is 0 degrees Celsius and 1 atmospheric pressure of 760 millimeters of mercury. It's the only one you really got to know, because it doesn't. It's a standard that we utilize for research purposes, if you will. And then finally, the one that we're familiar with is the body temperature of 37 degrees Celsius, whatever the barometric pressure is and whatever the saturated water vapor is. Putting them all together, this is a little chart that is there. I don't know what to tell you beyond that. It's exciting, but those are the different conditions you end up having. The example that where this comes into play is, remember when we did the spirometry in 1050? I had one of your volunteers, I forget who it was, do the measurement. We were measuring at ambient temperature, pressure, saturated, ATPS. We want to know what it is at BTPS. So there's actually a conversion we have to do to get back to that point in time. The good news is the computer does it automatically. But if you were to manually have to do this for some reason or other, there are conversion factors that we can end up doing that. There are various ways to measure pressure. We typically use an aneroid barometer. You can also use a mercury barometer to derive atmospheric pressure. Now it's actually probably even an electric barometer. I'm not sure how they work, but and then airway pressures and blood pressures, as you guys know about the sphygmomanometer. When we were measuring that pressures in the arterial system, we were using something called a strain gauge. But there's various ways you can end up doing this. This is a mercury barometer, Evangelista Torricelli. As we push down on this column of mercury, or this reservoir of mercury, it pushes mercury up, and you can calibrate what the barometric pressure is. And that's basically the way the barometric pressure was done for years and years, until we discovered that mercury probably was not a good thing to have around. Now we use an aneroid barometer, and when it'll be Mary next semester talks about cylinders. This is the way most gas cylinder pressure is evaluated. Whatever the pressure is, it applies on a spring, and there's a little needle then that moves to tell what the pressure is. This is an example of a pressure manometer that we would use on a patient's airway. So one of the tests that we're going to actually do, I think you guys do them on each other, is a maximal inspiratory and a maximal expiratory pressure. A little manometer to be able to measure that. Never seen one of these before, right? And this is that strain gauge I was talking about. It's a wire. And for right now, it's what's used to measure blood pressure in a patient with an invasive line in place. How it works is really just as pressure is applied to that wire, it changes the resistance through the wire, changes the current. Let it go at that. Okay. Strain gauge is the name of it. Now, we talked about these previously, and the ones that I want you to know are 760 millimeters of mercury, 1034, and 14.7. And that's what we typically utilize. It says that's a British measurement, but we use that typically in the United States also. Now, you go to foreign countries, they're going to use things like kilopascals. If you listen to the weather, they typically report it in inches of mercury. Why? Just the convention locally. We're going to end up using those three. So those are the three that we'll need to convert between. We can forget the rest. Again, how we end up doing this, if I want to convert 105 feet of water to pounds per square inch, there's probably a conversion factor that applies to 1 atmosphere, and 105 feet of water times 14.7 divided by 33.9 will end up giving us 45.5 psi. So that's going down probably about 3 atmospheres. Pretty significant. But this conversion is going to be one of those three that you'll have to manipulate. Is everybody good on this? If I gave you a problem on how to do and how to walk through it? I'm seeing nods, so I'll guess that's yes. Pardon me? I can't hear anything yet. We won't be giving you a chart. Those are the three that you have to know. All right, I beat that horse dead. I don't know why I got that there. So let's compare gas. What is similar about all gases and what is different about all gases? There's multiple gases that we'll be working with. The ones on the left there are the more common ones. And density is basically one factor that we can use to determine what is difference between the various gases. And I think before we went through how to calculate that out. Anybody ever heard of Avogadro's law? It goes back a ways. If you took any kind of a high school or college chemistry course, I'm sure they talked about it. But basically, 1 mole of any gas under the same conditions of temperature and pressure, i.e. STPD, will contain the same number of molecules and occupy the same space. So here I have it at STPD, and the same number of molecules are present, same number of volume is present. And what an ugly looking guy. I don't know, maybe it's just me. He was never married? Probably to some guy named Carl. When we talk about a dozen eggs, we know that the dozen eggs are the same number, 12. They occupy the same space as an egg carton. What is different is the mass that is present for each of the gases. Same is true back here. Oxygen has a different mass than air does. The number of molecules in 1 mole is 6.02 times 10 to the 23rd, which is a huge number of molecules that are present. The space that they occupy is 22.4 liters. Okay? There's one exception to that, and it's CO2, and that's something like 22.39 or some little variance in that, but it's pretty close. So what the heck is a mole? Well, it's that. It's the number of particles It's the number of molecules at STPD. Got to remember that part of it. The volume is always 22.4. What is different between the individual gases is the molecular weight or mass that they each have. So this mole thing is based on the mass of the molecules. And we know that every molecule has a different mass. And how do we find out what this mass is? Well, we take a look and see what the elemental, what the elements are and how many of them there are. We go to the periodic table, we find the masses, and the mass on the periodic table is in something called atomic mass units, and we add them up. And then we change AMU into grams. So let's look at an example here. Yeah. One molecule, pure carbon, has a mass of 12 grams. An atomic mass unit, let me back that up. If I go and I look at carbon on the periodic table, it's going to say it has a mass of 12 atomic mass units. 1 mole of this then has a mass of 12 grams. Okay? Here's some examples, just for Nikki. O2, what's the element? Oxygen. How many of them? What's the mass of each mole, or each element? 16. So 2 grams, or 2 AMUs times 16 is 32. We just changed the units from AMUs to grams. What else can we say about that 1 mole of oxygen? It has a mass of 32 grams. And what do all gases have if it's 1 mole of it? Those 2 facts are true for every gas if we're talking about a mole of that gas. A mole is nothing more than a quantity. And the quantity is based upon the mass of the individual elements. So what about carbon dioxide? We have 2 oxygens, 1 carbon. We add them up, we have 44 grams. So 1 mole of carbon dioxide occupies 22.4 liters. That's 6.02 times 10 to the 23rd particles and has a mass of 44 grams. Now that volume that we're talking about is only true for gases. These next 2 are not gases, but the same rule applies. We want to talk about a mole of potassium chloride. What do I need to do? Identify the elements. Potassium and chloride. Figure out what their gram molecular weight is. Look at the periodic table. Add them together. Change the units to grams. So if I wanted to make up a mole of potassium chloride solution, I would need to have 39 grams of potassium and 34.5 grams of chloride. Mix them together in solution, and I have a 1 molar, oh boy, solution. It's 1 mole. Am I missing something here, or is this like still not making sense? Bueller? You're fine? Okay. What about sulfuric acid? What's my elements? 2 hydrogen, a sulfur, 4 oxygen. Add them all up. 1 mole of sulfuric acid has a mass of 98 grams. Also has 6.02 times 10 to the 23rd particles. The volume it occupies will be different because it's not a gas. And we already went through these two. Okay, so that's how determining how the mass of a mole of a substance. Here's three gases, neon, oxygen, and helium. They all occupy the same volume. They all have the same number of particles. What differs is the mass that each has. In the case of neon, it has a mass of 20. Where did I get 20 from? I looked on the periodic table. Oxygen has a mass of 32, 2 times 16. Helium has a mass of 4. Now notice, do you remember how I calculated out density? Mass per unit volume. What's the denominator for all three of these? 22.4. So the only thing that varies is their masses. Who will have the greatest density of the three? Oxygen. It's got the most mass. Okay. Okay, there is some stuff in Cybersyn if you happen to have picked up that book. It was optional. And there's a periodic table that you can get from anywhere. So density of a single gas we just went through is pretty easy. You just divide the mass of that particular gas by 22.4. And you can see that carbon dioxide, because it has a higher mass, has a higher density in the process. Again, these are all measured at standard temperature and pressure dry. And again, technically CO2 is 22.3 liters, but let's just make life easier. What about for helium? What's the gram molecular weight? 4. 22.4. It has a density of 0.18. And you can see that's why it's used in combination with oxygen to reduce the viscosity in Poussey's law to make the pressure needed to drive the gas through the tube less. So there's my oxygen, there's my carbon dioxide. You can see that it has same number of particles, same volume, different masses, different densities. All right, lastly, and this is probably the hardest part that we'll talk about today. What if I have two different gases together? Well, first of all, you need to find out what percentage of each gas is of the total. Second, I find the gram molecular weight of all constituent gases. And then what I do is I take the first gas, multiply it by its percentage, and this would be the gram molecular weight. What's the gram molecular weight of the second? Multiply by its percentage and divide the whole kit and caboodle by 22.4. I think we need an example. Density of an 80-20 heliox mixture. I have 80% helium, 20% oxygen. What's the overall density of that mixture? Take the gram molecular weight of helium times the percent of helium, the gram molecular weight of oxygen times the percent of oxygen, and then divide the whole thing by 22.4. We said what did we say the individual densities were? 0.18. Okay, that's what I was looking for. So we said this one was 0.18 by itself. This one was 1.43 by itself. So I'm making them into a mixture. How much did I change the overall density? 4 grams is what the gram molecular weight is. Multiply it times 0.8. 32 grams for oxygen times 0.2. Do the math on those. Add them together. Divide by 22.4. We find that the density is significantly less than breathing pure oxygen, which is, again, one of the reasons why we use this mixture in patients who have high airway resistance. It becomes less viscid of a gas, and according to Poussin's law, that should reduce the pressure required to push the gas through the tube. I'm going to put that down. I would anticipate seeing a problem of this nature on the next test. Just 'cause. Everybody see where we got the numbers from? All right. Can I go? And again, there's different problem sets there that are there. There is some of this information in Egan if you kind of want to review. And again, that optional text, Cyberson, has a lot of problems also. If this is something that you're struggling with, there's some more practice problems there. And I will stop there.